process overall includes establishing the estimate scope. What are you trying to accomplish? Figuring out a technical baseline and ground rules and assumptions. What is it you're going to be building or estimating? Collecting the information to be used as source information for the program estimation. Step 4, actually estimating the size of the software in terms of things such as how much functionality or how many lines of code or things like that. Step 5, preparing the baseline estimate, so we have an estimate and we're halfway through the process. Step 6, reviewing and verifying and validating these estimates so that we can verify that we have something that makes sense. Step 7, quantifying risk and risk analysis so we can see what the risks are and where we should really look at this program happening. Step 8 is actually generating a project plan based on the estimate that will map back to the estimate. That's an important step many people skip. Step 9, document the estimate itself and lessons learned so we have a baseline of how we got there and how we can do better in the process next time. And then step 10 is tracking the project throughout development. By following a 10-step process like this, more software projects can be successful. Some people say that this 10-step process is too much work. They just got to get the estimate done. Well, I suggest to you that if you take these steps and you can compress them significantly, and you can actually do this in an afternoon for a smaller system. But by doing these, you'll end up with more successful projects and more confidence in your estimating processes themselves. Looking at process number 1, step 1, estimating the estimate scope. In step 1, we talk about what is it we're trying to accomplish. Is this a rough order of magnitude estimate we're going to use just for making overall decisions? Is it worth going forward and looking more or not? Is it a concept level estimate where we're trying to come up with alternative concepts? An affordability estimate where we're trying to find the most affordable alternative for a system? A detailed plan that we can actually implement from the estimate, and different kinds of estimates so that we have some kind of a goal of what it is we're trying to accomplish. Now, the purpose of this is to provide a baseline to make decisions for management and also to measure ongoing efforts against. Having an estimate scope helps us to reduce the number of misunderstandings and contradictory assumptions later on as well, so we know what it is we're trying to accomplish. And of course, that estimate should be a living document. Sometimes I see people taking an estimate and then starting a program that has nothing to do with the estimate, and funny thing, it overruns. You know, when the programmer changes, the estimate should change. Now, of course, if you're doing appropriate risk analysis, you may just have changed your probability, but the estimate should be looked at whenever there are changes to the system scope. Looking at what an estimate is, an estimate's the most knowledgeable statement you can make at a particular point in time regarding the effort, the cost, and the schedule, the staffing, the risk, and reliability. And estimates get more precise as the project goes on. And a well-formed estimate, a good estimate, is a distribution. So we know the most likely, we know the 90% probability, etc. And again, I believe that having a probability associated with the estimate is critical to having viable estimates. Looking at the estimate as well, we need to understand what's included and excluded. And you can include or exclude whatever you want. The important thing is ensure that it's been defined is what we're intending to include and what we're intending to exclude. When someone just gives you a number and doesn't say, well, this includes or excludes external testing, installation, etc., you don't really have a good estimate. Again, looking at the scope in a little more detail. What are we trying to accomplish? Is this the worst case scenario? What if everything goes wrong? Is it a best case scenario? What if everything goes right? A rough order of magnitude. Are we doing risk analysis? And we always should do risk analysis, but sometimes our early estimates are just getting a sort of a number. What kind of system is this going to be? Are there going to be several subsystems? Are we working with an existing system that has several existing programs that need to be modified? Is it an agile system where we're going to be coming up with the estimated range of effort and schedule for the overall system where the details haven't been defined yet? Is it all new? Is it modified? Is it we using commercial off-the-shelf systems such as databases or graphics package, etc.? And are we building this or generating from code? All the things that are good to know before you start doing an estimate. Now, people usually know these to some level, or at least have assumptions on them. The key here is just to write down those assumptions. Now, talking about assumptions, step 2 is establishing a technical baseline, the ground rules, and the assumptions for the program. So overall, the point is to come up with the functionality we believe will be included in this system. Or it can be a range. Perhaps we have a range, for example, in an Agile system. We'd like to have a minimum of X amount of functionality, and it could go up to Y. If the detailed functionality isn't known, and it often isn't early on, ground rules and assumptions identifying what we believe it'll be, and a range as well, so we can get a range of risk. Issues of commercial off-the-shelf software and reuse should be documented. And those ground rules and assumptions really form the foundation of the estimate. The technical baseline itself identifies that core functionality, the key modeling inputs, the key characteristics that we can model, size information about how much software is it, and different information, for example, if there is a plan for several iterations or if it's going to be agile or whatever, identifying those characteristics that have already been determined if you have them. Ground rules and assumptions is a place where people often get into trouble. A ground rule is something you got to do. For example, the software's got to support Windows and Linux. The software's got to work in the latest browsers or whatever it may be. Those are things that just have to happen. An assumption is a little different. Assumption is something we assume will happen or assume will be there. So an assumption is something in the estimate that isn't something that if we do it or not, the project will be killed or not, but it's an assumption about what we believe this project is. For example, the assumption this project will have about 27 different input screens. Assumption the project will have to work over a heterogeneous network or whatever. What's known and what's unknown, and things we don't know, it's good to identify the list of things we don't know and would like to know. Anything regarding scope, what's included, what's excluded, and regarding the characteristics of the program, where you got them. Did you interview someone? If you did, who it was and what you learned. Looking at assumptions, I can't tell you how many programs I've seen over the past several decades where people got in trouble because they defined assumptions that weren't realistic, and then they tried to do a plan that wasn't realistic because of the bad assumptions. So I believe spending time looking at the assumptions is a important and part of the estimating process. In this little diagram here, we can say, one, identify the assumptions, then rank the assumptions based on the impact of the estimate. What if this assumption is wrong? Find those assumptions that, if they're wrong, are going to cause a big problem in the estimate. Rank those risky assumptions, and then do a trade-off analysis. Try to clarify the assumptions where you can, and do a risk analysis based on what if those assumptions go wrong. When people just take assumptions and don't look at the risk of those assumptions and don't look at the potential impact, they often end up with estimates that aren't viable. In step 3, collect data. Now, the assumption is that you've already got some organizational data, so if you don't, go collect some of that. But we're really talking here about more program specifics. Collect information about this particular program. For example, if it's an existing program, it's going to be modifying 3 systems. Do you have sizes for the existing systems? Can we have any measure of or any assumptions about how much will be redesigned, re-implemented, and retested, etc.? Use forms when you can. And document not just what you got, but why you got it and who you got it from. Identify the range of best case, likely case, and worst case. Identify what is required or just desirable. Try to get those things that are required. Face-to-face interviews with stakeholders can be really helpful in collecting information as well. And then grade the information to look at the confidence. For example, if you're using an external database for sizing, something like Icebags or the Gallup database or something, it might be that we find some data points that are in some ways similar but are significantly different due to reuse or something. Identify and rate the confidence you have on those being viable. And finally, normalize any data so that you have a process for having the data all in a single format. Some data might include, for example, the program management, some might not. And it's fine as long as you know, but part of the process of normalizing, so you put it all into one way of looking at it, whether it's in or out, so you know what's in the data the best you can. People get into trouble sometimes just because they have 2 data points that sit side by side. They may not be because of the same outcome. It could be that Project A ended up taking 3 years, and Project B ended up taking 3 years, but they were for different reasons. And Project A, there were 3 restarts. Project B was just a larger program, etc. So identify how those tie into your data. Now, if you look at other data and the impacts of data, here's a plot overall. In this example here, we've got programs between 230 and 300 function points, and there are 291 of them. Well, is that good enough for estimating a new system? You know, in this example here, the data points haven't been normalized. So here we got data points. This one doesn't include testing, so we got problems. This one has only got code and tests, so we've got problems. This one here, the requirements were excluded, etc. The point here is that the data should be normalized and put into some common format to make the job easier and more consistent. To have a program data point that only has code and unit test, if you know that, it's a good thing. You can normalize, but if you don't know that, you've got kind of mush. Data comes in all shapes and sizes. Development and modeling involves things of just making things similar. For example, as I said a minute ago, if the quality assurance or if the customer's time in working in an agile program or something is not included, that's fine. Document that. But if you're trying to estimate a system where the customer's time is included, or quality assurance or whatever is included, come up with a measure from prior programs of the ratio of how much you should be adding or subtracting from the data to come up with that. Gallup has some standard numbers, and you can find them on the internet as well. The obvious things, inches versus centimeters. What about overhead? Is this just the direct costs of paying the developers, or does it include the facilities costs and the secretarial support and other things like that? And again, the point is you can do it any way you want. The point is to know what you have and what you're doing, and to document that so that you've got something consistent. So when you're all done, you got a number that says $1 million. You know what $1 million means. Looking a little more at actuals, what's included or excluded. When you got an actual, and this hopefully has been done before it was put in your database, what activities and phases were included or excluded? And the point is to try to get them consistent. Even if you didn't collect the data on program management for a particular program, using that data point might be fine. You come up with a ratio. Or remove program management from all your data points. There's different ways to do it. The point is to do it somehow. And more of the same, the labor categories and activities might not be included as well. Other things that are good to know, schedule issues, for example. Was the program a start-stop? Would they have to restart 3 times? Were there hard-hitting resource constraints? Did they not have the people they needed? Were the requirements so volatile that the program was more costly? Did the manager have an objective to get the software done as quickly as possible or at the least cost? And how exactly were things done? Any of these forensics you've got are wonderful. If you don't have any of them, of course, SEER provides knowledge bases, and those have been normalized, and you can depend on those. But for looking at your own data, it's important to understand what you have and what you're trying to get. Step number 4, estimate and validate the software size itself. We like to spend a significant amount of time on sizing. It doesn't have to be a lot of time, but if you're doing, for example, a function point approximation, you can do an approximate count. Oftentimes at Gallup, we'll use a prior system and say, hey, this is a little bigger, a little smaller, analogy kind of systems. We do recommend estimating a least, a likely, and a most range instead of a single point because software tends to grow. Lots of ways to do this. Expert opinion, a little scary. Analogy, look, we had a system X and it was Y large. We believe this one will be 30% larger. Doing statistical methods of coming up with software sizing, and there are numerous other ways to do this. And size is probably the biggest driver on a system. Within a single computer program, the effort and schedule vary in proportion to the size. The better the size estimates, the better the effort and schedule estimates. Now, again, this isn't a cop-out. Up front, you might not know the size well, but you should know a range of least likely and most. If you don't, SEER can come up with that for you and help you to figure out how big it might grow to if you know a size at a particular point in time. SEER supports many sizing measures. The real point is to come up with something that you can actually estimate well and that you can track when you're all done. For example, many people use lines of code. It's gone out of fashion in some industries, and other industries it's still widely used. Function points, which are measures of the software functionality based on rules, are an excellent way to do things. There are looking at special things to count commercial off-the-shelf work, the number of objects, cosmic function points, which is another method of function points, the number of use cases being used in web pages, story points, and other methods. The real key here is to have something that will relate to software size. Here's an example of where people had not normalized their software size. Maybe they had, but they didn't admit to it. In this example, this is a line of code job, but the people said that it was 1.6 million lines of code. And they, when it was actually looked at in detail, it turns out 23% of those lines of code were comments, 25% of them were blanks, 6% of them were debugging code, and actually only 46% of those were actually lines of code that required any work. And that's the kind of lines of code that SEER would take. So it's important when dealing with sizing and size definitions to have people understand what you're working with. Logical versus physical lines, is it number of carriage returns versus number of units of work or whatever. And again, we don't mind so much how you do it. SEER can handle them all, but we do recommend that you know what it is you're doing and why you're doing it. For reuse, so we see people often saying, oh, we're just going to reuse all this software, and that's a good thing. Reuse is a good thing. And we're going to do some innovations and modification to some of our software. But it's important to look at how much of the pre-existing software will have to be reworked and how much it would have to be retested. By ignoring this, we can actually underestimate systems dramatically as well. And when it all comes down to it, the size should be boiled to an effective size. How much work do you have to do? You might have a 10,000 function point system. If you've only got to add one report, it may only be 7 or 8 or 10 function points of work to add the report. But then if you've got to go back and retest the system, that could be another several hundred function points worth of work. And of course, if you're using SEER, it computes all this for you. The point here is to come up with and describe how much is new, how much is existing, how much is off the shelf, and then how much of it's got to be reworked. SEER prompts you with all this and provides knowledge bases for these things. And but the more you do, the more work more time you can spend doing this, the better your estimates are going to be. Of course, these are all at ranges again. Step 5, preparing baseline estimates. I described an estimate a minute ago. An estimate's the most knowledgeable statement you can make at a particular point in time regarding effort, schedule, staffing, risk, and reliability. And a complete estimate includes not just the estimate, but the probability, the range of probabilities. There's a 70% probability this will take X time, for example. Lots of ways to estimating. The most popular one is, unfortunately, is guessing. There's no basis or substantiation, and it's usually wrong. But people often do that, and then they go along with projects that end up getting in trouble because they weren't right in the first place. They weren't even in the ballpark. Analogy is a good thing. By looking at existing systems, saying, well, this is a little tougher, a little easier. Expert judgment, hopefully that's a better form of guessing where you've got experts that have done this before and have better opinions. Top-down, estimating the system at the top and then decomposing it. Bottoms up, looking at the system, all the little pieces, adding them together, some risk there, and forgetting about the things that make the software not do what it shouldn't do. And then things like cost estimating relationships, mathematical equations to look at what the software might take, and comprehensive parametric models like SEER. The comprehensive models can do a better job because they can describe characteristics of systems in a way that most other techniques can't. Here's an example of a system for a given size, complexity, and technology. There's a range. There's a minimum time to get the software done, and there's not much you can do to get it done any faster, except perhaps don't test it as well or skip some steps in the process, which is going to bite you later. There's also an optimal effort. Optimal effort is using a little bit longer time and a smaller staff to get things done a bit more efficiently. There's the worst case where you expand the work, you use too much schedule. I've seen projects have too much schedule and nothing gets done because people aren't under any constraints. And there's a reasonable range for the estimate, the minimum time being probably the shortest schedule, the optimal effort being the most efficient one if you got the time. Again, programs like SEER help you figure this out. This is just looking at it another way, reasonable plans and inefficient plans and projects that are going to fail based on the characteristics. Now, I also believe that total ownership cost should be looked at, not just development cost. Well, development cost and schedule are important. What's it going to cost you over the long haul? In this example here, the blue is the development cost. The maroon and those other colors are showing different levels of maintenance. Add those all together, and the total ownership cost may or may not make a system viable. Many times, a return on investment analysis will show that a system should not be done because the total ownership cost will cost more than what it'll save. generate the estimate, of course. Focus on the inputs. Make sure you've got the best you can on the inputs. Focus on the outputs. Do a sanity check. For example, in SEER, you can plot and see how your estimate compares to others. Step 6, review, verify, and validate the estimate. Now, we've got an estimate here, but it's important to go back and look and make sure we haven't done anything naughty. Ideally, the validation to be done by someone who wasn't involved in generating the estimate in the first place. Looking at the assumptions and verifying that they're viable. Looking at the ground rules and verifying they've been supported. Looking at risks and the identification and how the handling of risks was handled in the estimate itself. Performing cross-checks. Cross-check estimates, and this is an example of SEER that can actually do a cross-check in a number of ways. Looking at other programs that are roughly analogous, how does it compare? This one here looks like it's spot in the middle. It's good. Using things like our Project Miner, which can do a completely data-driven estimate, our scatter plots to show what happened in this program and how that ties to other programs. Here we see trend lines out of our databases showing where the programs may be. Now, the point is that if the project looks like it's much more efficient or much less efficient, it may be true. We're not saying it's not true, but why? Going back and finding out why. If this project looks like it's the most efficient that's ever been done, how are you going to do that? Or is it just optimism? Optimism is one of the dangers in estimating a software. Does your size estimate make sense? Look for the developer's gut. Don't rely on it, but look at it as a secondary approach. Does it make sense? Is this 200 function points? Is this 10,000 lines of code? Quantify risks and risk analysis, step 7. Risk can produce losses of time, quality, money, control, and understanding. Risk management addresses both the internal and the external threats to the software. For example, estimating and sizing. If you miss a lot of functionality, that might be one of the significant risks. Risk can be specified and can be manageable, and statistical risk should be part of the project. For example, in SEER, we can provide the least likely and the most sizes or personnel capabilities or whatever, and it will use that for uncertainty and risk analysis. Here we can see a small example of an output. The goal was to have a schedule in 20 months. It looks like there's about a 30% probability on the chart on the right of hitting that 20-month schedule. The goal was to have $1 million in cost. Looks like there's about a 25% probability of hitting that cost. Peak staff of 5 people. You have plenty of staff. The problem is you just don't have enough time. So looking at these things gives you the ability to understand if this is a viable program plan, and if you need to go back and redefine the program, or if you need to go educate the stakeholders, or if this program needs to be killed. And uncertainty involves looking at the best cases, likely cases, worst cases, and running statistical analysis, which is done inside of SEER. Here's an example. In this case, the most likely estimate is 3,170 hours. Schedule 20.86 months. That's most likely what's going to happen. There's a 20% probability, 80% chance of exceeding 2,266 hours and 14.9 months of schedule. Look at that. It's almost 5 months or 6 months of schedule difference. But that says there's an 80% chance you're going to exceed that. There's some chance you'll hit it, but an 80% chance you'll exceed. The question is, are you willing to take that much risk? And of course, if you look at the worst case, this example here, there's an 80% probability this won't take more than 4,567 hours and 30 months. Now, is it worth building this program if it takes 30 months? It may be that the window is too long. Maybe it needs to be de-scoped. The point here is to have the visibility into what happens, what will happen, and why it'll happen so you can make the right management decisions. Okay, looking at how your program compares to other programs, the little scatter plot on the right has got our program in there, and it's got a bunch of analogy programs. We can see our little program is in the middle there pretty much. Looks like that's pretty safe. That one probably makes a lot of sense. Step 8, generate a project plan. One of the things I see people doing occasionally is they'll have a beautiful estimate, and then they'll build a project plan that has nothing to do with the estimate. To me, that's a critical error. The estimate should trace right into the plan. And if it can't, then you've got a problem with the estimate or you've got a problem with the plan. Sometimes managers don't want to hear the answer. Maybe the answer is it's going to take 30 months and they want it done in 2 years. And just building a plan for 2 years when it's a minimum time, a 30-month project, it isn't going to work. So develop a project plan based on what will actually happen. Here's an example. Seer works with things like Microsoft Project and Primavera and other project management systems. We've got a Seer estimate that generates an actual task-by-task plan inside of one of these programs. That can be extremely useful, so you've got an estimate that does trace back to the plan. Step 9, document the estimate itself and the lessons learned. And the important thing about documenting the estimate is so you can see later on, hey, what happened and why it happened, and if it was right or not, and if it was wrong, to be able to modify it along the way. For example, if you had assumptions that turned out wrong, to be able to modify the assumptions and re-estimate. And building lessons learned is critical to helping to improve your estimation process. Lessons learned in the estimation process, as well as lessons learned about the software and the sizing and those kind of things. Step 10, track the project throughout its development. Step 10, again, the estimate gave us a baseline, and as the project progresses, we can see how we're doing compared to that baseline. The useful thing about this is, assuming we're keeping on track, if we're not on track, using management capabilities to go in and find out what's wrong and figure out ways to fix it. Traditionally, you can look at a program and see if it's healthy or not based on how it's performing compared to the plan or budget. In this example here, we can see, this is a Seer output, we can see a number of things. We can see the schedule is yellow, green, yellow, or red, so it's behind, but it's getting better. The cost is behind and getting worse. This is a bad thing. The size growth is green and good and getting better. But look at the defects here. This is actually tracking. This is optional. You don't have to do it, but it says the number of defects are bad and getting worse. Here we can see Seer's estimate of the defects. The red line represents the estimated number of defects to be inserted in the system. The blue line estimates the defect removal rates. Now the green line represents the actual, so he actually had more defects than were estimated, and that little purple magenta line represents defect repair. So here we repaired fewer than the blue line, and we found more than the green line. This project's probably in big trouble. That's one of the key parts of earned value or performance monitoring that make sense for software in addition to traditional things. Defect insertion and removal rates your project might be going on the tubes and you don't know it if you don't look at this. There's a little more on looking at the earned value. Here we can see this baseline program is supposed to be done here at the blue line. Looks like it's going to expend a little bit. The program's getting a little behind in a number of ways. Looks like schedule is going to be 14% more than we budgeted or planned, and the cost is going to be about 9% more. In digging into this thing, why is this happening? What can we do about it? But if nothing else is done, it looks like this project will overrun. Poor estimates have dramatic impacts on projects. They're one of the root causes of project success or failure.